All right, so here we're starting chapter 5, and in 5.1 we're going to talk about polynomial functions. We're going to talk about how a degree affects what a function looks like, how to determine a degree, and first and foremost, how to name and classify them. So the standard form of a polynomial function in general is this. I'd write this down even though it looks kind of ugly. Basically what this represents is that any polynomial I write by arranging the terms by degree in descending order. So what that means is an example. Let's say I have the function 4 minus x to the fourth plus x minus x squared. To have this function in standard form, I would rearrange all my terms to have my degree in descending order. So notice now how I have x to the fourth as that first term, then the x squared term, then the x term, and then that constant number. Next, we're going to learn how to classify polynomials. So we name polynomials by its degree and by how many terms there are. So if the degree is 0, or basically I don't have any x, I call that a constant polynomial. If the degree on x is 1, it's linear, 2 would be quadratic, 3 would be cubic, 4 would be quartic, and 5 would be quintic. Now we could keep going with higher degrees from here, but in this class we're really not going to work with anything higher than to the 5th power, so we'll go ahead and stop there. The other way that I name polynomials is I also name it by the number of terms. If there's only one term, I call that a monomial, and you could see an example there would be something like 3x squared. 2 would be a binomial. 3 would be a trinomial. And for whatever reason, I don't know why, but people that invented this just stopped making names after 3 terms. So if I had something like 4 terms, I would call that a polynomial of 4 terms. If I had something that had 10 terms in it, I would say a polynomial of 10 terms. I really only have fancy names for 1 through 3. So in the first couple examples here, I want to write the following polynomial in standard form and classify it by degree and number of terms. In part A, I have 3x plus 9x squared plus 5. So what I'm going to do first is I'm going to rearrange my terms. So now my function is 9x squared plus 3x plus 5. And now to name it or classify it, I look at the highest degree, which is 2. So this would be a quadratic. I see the number of terms. I have 1, 2, 3. This would be a quadratic trinomial. And that's how I'd classify it. In part B, I have a lot more terms. I have 4x minus 6x squared plus x to the fourth plus 10x squared minus 12. So what I want to do first and foremost is I want to combine like terms. From there, I'm going to combine like terms, rearrange everything from degree in descending order. I'm left with x to the fourth plus 4x squared plus 4x minus 12. Now, I can look and see, okay, my highest degree is 4. I'll call that a quartic. I have 4 terms. I will call this a quartic polynomial of 4 terms. So another key concept here is that the degree of a polynomial affects the shape of its graph by determining 1, the number of turning points. We'll talk about that more in some later sections. And the end behavior of the graph, which we talked about a little bit with domain and range. So what you'll do first, write down this chart, highlight it, star it. This is going to seem confusing until we do an example. The different kind of end behaviors that you could have is up and up, down and up, down and down, and up and down. And what determines that is the highest degree of that polynomial and the a value or the coefficient in front of the x value with your highest degree. So again, I'll pause this video, write this chart down very clearly, and highlight it. So in an example, let's determine the end behavior, or describe the end behavior of f of x equals 4x cubed minus 3x. So to determine the end behavior, I first look at my a value. My a value is positive because I have positive 4. And my degree is 3, so my degree is odd. So if I look at my chart, when the a value is positive and the degree is odd, my end behavior will be down and up. Now you might be reading that and thinking, what the heck does that mean? If I graph that function 4x cubed minus 3x, I'm going to get a function that looks like this. So what I mean by down and up is that to the left of that graph, I'm going down for forever. But as I go to the right of this graph, I'm going up for forever. So that's essentially what that means. Finally, the last thing that we are going to do in this video is use differences in our outputs to determine degree. So here in this chart, what is the degree of the polynomial function that generates the following data? So I have a bunch of coordinates, and I don't really know when exactly this would be useful. It is kind of cool though, but let's say I didn't have a graphing calculator on hand, but I needed to determine the degree of that polynomial function. This is how I could do it algebraically. What I'm going to do is I'm going to look at my y values or my outputs, and I'm going to look at the differences between all of them as I go to the next one. So going from -1 to -7, I would have to subtract 6. That's -6 difference. Going from -7 to -3 would be +4. -3 to 5 would be +8. 5 to 11 +6. 11 to 9 -2. And 9 to -7 -16. So if all of those values were the same, this would be a linear function. Clearly it's not, so I'm going to have to do this process again. I look at the differences of these values. Going from -6 to +4 is +10. Going from 4 to 8 is +4. 8 to 6 -2, -8, and -14. If all of these values were the same, I would say this is quadratic. Clearly they're not, so I need to do this again. Going from 10 to 4, I have -6. 4 to -2, I have -6. -2 to -8, -6. And -8 to -14, -6. So all of these values are the same, so I could say that this is a cubic function, or finally, the degree of this polynomial function is 3.